Hello, hello, hi everyone. We're gonna go ahead and start off with our last part of this unit one, um, continuity. Now, the gimmick with this section is that we're gonna go ahead and learn what qualifies a function to be continuous, right? Now we know some, or we should recall some classic ideas where, dividing by zero, that's going to go ahead and be discontinuous. Not all the time, but piecewise functions um, can also be discontinuous as well, but it's not a guarantee. Here it's just a maybe. Another discontinuity that we can go over is taking a negative value inside a square root. We know that you can't do that, and that would be discontinuous. So there's things like that. So we know more or less about these rules for these functions on what we can do with them to make them a valid entry or not. Now, we're going to go ahead and discuss them from their limit definition. So there are three conditions for continuity at x is equal to some numeric value a. One, f of a is defined. That is, that the function has a y value at x is equal to a. Next is that the limit as x goes to a exists for that function. And again, just reiterating, the limit means that from the left and from the right, they do match up. Now, you don't always have to check this second condition, because sometimes, if you're dealing with like a classic polynomial where really it's not known to be not continuous, you can go ahead and she's not doing that step. But you're gonna see that for for all but one of these, we're gonna go ahead and perform that step. And then lastly, that limit as x goes to a for that function and just that function output equals. Okay? Now, polynomials and rational functions are continuous at every point in their domain. The domain is the set of x values allowed in that function. So this is heavily alluding to the square root thing I said earlier. We say that the square root is discontinuous because you can't take a negative entry. However, if we limited the square root's domain, so for example, we said this function only from 0 to infinity, then it wouldn't be um, discontinuous in that way because we've limited its domain and we chopped it off where it would be considered discontinuous. So things like that. There are three types. There's removable discontinuity at that specific entry. So that means that the limit exists, but it does not equal f of a. So that's going to be removable in that it's almost I think your homework is maybe also going to call this like a hole. So there'll be a hole in the function where it just literally disappears. And then we have the jump discontinuity where it says that these limits both exist, but they're not equal. So that's going to be a jump discontinuity. Means that, as we come from one, let's say this is our f of x on some function, we say that it's coming from the left and then from the right, it doesn't meet. And maybe one of these is an open circle, one of these is a closed circle. It jumped, right? The function line jumped from here to here. So that's why they gave it the tag of a jump discontinuity. And that the both limits we can see visually will exist. It's just that they don't coincide with each other, they're not equal. This is not to be confused with, though, an infinite discontinuity. So an infinite discontinuity is when that limit from the left and that limit from the right are an infinity. And now this can be, sort of jumping. It doesn't matter if they're both infinity, if one's negative and one's positive. It's just called an infinite discontinuity because they trend from each other to infinity, basically. All right. Now, Let's start off with the first example. So determine whether the function is continuous at x is equal to 2, f of x is equal to x squared minus 4 over x minus 2. Okay? Well, let's check the first guy. So we're checking the first guy, and we're checking f of 2. And we're going to see a problem right away. 2 squared minus 4 over 2 minus 2. Well, we do indeed get 0 over 0. So right away, it breaks the rule at that first condition. We could technically just be done. Okay, it's discontinuous. Boom. But we need to practice doing all of these conditions to make sure we have a better understanding of them. So let's go ahead and do number 2. Number 2 is asking about the limit. So the limit here, as x goes towards 2, x squared minus 4 over x minus 2. Now, we already tried that substitution idea with limits, technically within 1, and we got that 0 divides by 0. But that does lead us with more information about what we can do to actually get that limit and double check that it exists or not. So from here, or we can also use the difference of squares. So remember that that's a square, that's a square. Let's use difference of squares. Since for you guys, you're gonna be seeing like a review video more or less after you play this video. So I'll sneak in like a review-ish topics. So difference of squares is that idea, here let me write it, where we have x squared minus a squared, and that's gonna be equal to x minus a, x plus a. So that means we can write this as x minus 2 and x plus 2. And then bottom x minus 2. That cancels out, and then now we're just asking the limit as x goes towards 2 for the function x plus 2, which we can just use substitution, plug that right away, and we get the number 4. So that tells me that that limit exists for sure. No question about it. Step 3 is just checking if they equal, which we kind of can't even really check because we don't have a value here. So we can't really check. Can't check due to f of 2 not existing. Now, in conclusion from all of these, what can we say about its kind of discontinuity? Because we already show that this is going to be not continuous. Just looking at condition 1, we could already have left this question and been like, okay, so this question's not continuous. But what about, hold on, I'm sorry, I just realized I forgot to turn on my avatar for the virtual, or for the vertical people. Okay, right. For the vertical people. We're all vertical people. Well, you know what I mean. For the people that watch the video for vertical. Um, sorry. Um, what kind of discontinuity are you dealing with? They're dealing with a hole, a jump, or an infinite discontinuity. Well, we're not dealing with the infinite because none of infinity hasn't popped up at all here. So we're not dealing with this one. We could be dealing with a hole or removable, or we could be dealing with a jump. We're gonna go ahead and say that this is gonna be a hole. Now, it's not a jump because that limit does equal. We don't have to check the left and the right. We just checked it right away and we saw that we got a value. So we are to say that it's a hole. Now, granted, it's a little cheesy to say that there's a hole, but it makes sense. This limit exists. Now, even though this limit doesn't exist, it's the premise is still true. This does not equal this limit. So therefore, this is a hole. Or wait, let me write first. This is uh this is discontinuous. Continuous. Accidentally added an extra E. Or we can just say this is a whole discontinuity. Okay. And then the reason here, let me highlight just a little bit. So the reason for the whole is because these two guys don't match. All right, example 2. Determine where this function is continuous if this piecewise. Okay. Well, we see here that we do get this piecewise function at x equals 3. Yeah, so that is the breaking of this. So we can't just use one function right away. Well, let's still start off with actually just performing this function as you could like a pre-calc class or a college algebra class. F of 3, we use the top guy because it says to use it when x is less than or equal to 3, x is equal to 3. So negative parentheses 3 squared plus 4, that's going to be negative 9, plus 4, that's going to be negative 5. Okay. Now we have 2. And 2, we can't check that limit right away. We have to check it from both the left and the right. So I'm going to check the limit as x goes to 3 from the left. And I'm going to check the limit as x goes to 3 from the right for this function. Now, because of this, and it's going from the left, that means I can use the top part of this piecewise function, negative x squared plus 4. And for this guy, because I'm coming from the right of 3, I'm using the bottom part of that piecewise function. 4x minus 8. Then for both of these guys, I can use the substitution. I technically already did it over here, so I'm just going to skip to the answer, negative 5 for that limit. The bottom here, I need to do a substitution. 4 times 3 minus 8, that's going to be 12 minus 8, which is 4. So both of these limits exist, but they do not equal. So again, technically here we could stop. And we can say, okay, this is not continuous, whatever. But let's practice number 3 just in case. So number 3 says that the limit and that function output equals. We're kind of here at the same thing we were last one, where we can't really check this. Here we have to look this. But this time, due to the limit as x goes to 3 of f of x not existing. And then I kind of spoiled it a little bit what kind of discontinuity it is. It is a jump discontinuity. Okay. All right. I just had the urge to go, any questions? But it's an online video. If you have any questions, let me know, right? But it's a in person, right? Sorry, I'm being a nerd. Okay, let's keep going. Example 3. Determine where this function is continuous at x is equal to pi over 2. F of x is 7 times cosine of x plus cosine of x. Okay. Number 1, we have to see if this exists. F of pi over 2 exists. And it definitely does. It looks ugly, but we can do it. It's 7 times cosine of pi over 2 plus cosine of pi over 2, close. That first gets evaluated to be 0. 7 times cosine of pi over 2 plus 0. And then we kind of have a repeat where that would be pi over 2. And we're taking cosine of pi over 2 again, which is 0. And that means that's going to be 0. So that exists. We can't say it's not continuous there. Step 2, we check the limit as x goes to pi over 2 for this function. Now, right away, we can see that via substitution, we do get an answer, right? So I'm just going to use the substitution idea. Cosine's continuous. There's nothing that we cannot put inside of cosine to where it won't work. So we can just plug it in, and we kind of already did, so that limit's going to be 0. And then we'll check step 3 just in case, and step 3 says to make sure that f of pi over 2 and the limit as x goes to pi over 2 of the function equal, which they do. So this is actually not even discontinuous at all. It's just continuous. So continuous. All right, last one. Determine whether the function is continuous at x is equal to -1. We have fx here. Okay, so this is definitely discontinuous, and I went ahead and included a little graphic over here. So let's go ahead and see what this is. Now, step one, plug it in, which I can already see what's going to happen here. We have -1 plus 2 over -1 plus 1. That's going to be 1 over 0, which doesn't count, doesn't work. It's definitely discontinuous. Um, let's go ahead and practice limits. So I'm taking the limit as x goes towards -1 for this function, x plus 2 over x plus 1. And I need to simplify this a little bit. I could use polynomial division, or I could just sort of see that I can split this up a little bit and do x plus 1 on the top. And now become a that'll become a 1, and then plus 1 over x plus 1. Okay. Then I can use, or here, let me do this real quick. Okay, then I can use the limit loss to distribute this. So I know at the end of the day I'm getting 1 plus the limit as x goes towards -infinity of 1 over x plus 1. Then I have to remember some of my topics from the first part of this unit. Remember, when you see something like this on the bottom, let me give more detail. Remember, we have a power 1, and then it's going to be a minus a -1. They have the same thing being subtracted here. That we can use those limit. Actually, I don't know why I'm talking about them like I don't have them in front of me. We can use these infinite limit from positive integers idea here. But the gimmick is that that power is odd. So that means that it's a two-sided limit. So that means I have to split this up. And in splitting it up, I'll get 1 plus the limit as x goes towards -infinity from the left of this expression. And then 1 plus the limit as x goes towards -1 from the right of this expression, which will both produce 1 plus -infinity and then 1 plus infinity, which we know that if we were even to attempt this sort of concept, 1 isn't going to stop this from being -infinity. And same thing over here. It's not going to change this from being infinity. So we know that the